All right, Owls, this is going to be your next set of flip notes in our wave unit. Previously, we did parts of a wave by labeling those and the different types, and then we did sound notes, both focusing on the mechanical side of things. Now we're going to go and focus on the EM side of waves, and most particularly, we're going to focus on light and different wave behaviors. And behaviors just simply means how things act and how different waves act in different scenarios. All right, so use your flip note sheet that I gave you. Any questions or comments, please have them written down so in class you can ask me any questions. And let's get started. First of all, we're going to talk about the electromagnetic spectrum, also known as the EM spectrum. So there are 7 different types of EM waves, and each of those waves have different wavelengths and frequencies, and that's how they're distinguished, or that's how they are identified, meaning how they differ from each other is based on their wavelength or their frequency. Remember, as wavelengths change, as does their frequencies change. The spectrum is a diagram of 7 different types of waves, and here's a picture of this. Now, don't get confused with the pictures on the bottom of that. It's just showing you the distance between crest and crest, considering if you look at a radio wave, one crest to the next crest would be about the size of a football field, which is about 100 yards. But then if you look all the way down to the right of the spectrum and where there's gamma waves, their crest to crest is about the size of a nuclei, and if you don't know what that is the center of an atom, which makes that incredibly small and incredibly, that frequency is incredibly high. And we'll talk a little bit more about that later in class. So okay, so when I say general wave behaviors and light wave behaviors, all waves can act this way, but in the 6th grade curriculum, you are expected to understand some general wave behaviors, meaning behaviors that can happen with mechanical and EM waves. So the first 3 that you need to know are reflection, refraction, and diffraction. Refraction gets often confused with rarefaction from our labeling waves unit, so don't get messed up with that. But reflection is the bouncing back of a wave after it strikes a barrier. So light, that's how we see light. We'll talk a little bit more about that in a little bit. And then refraction is the bending of a wave when it hits a new medium. So obviously there has to be 2 different mediums happening with refraction. The mediums mostly have to be clear, meaning water happens often. And if you look at the middle picture where there's a prism, often that prism has to be clear for the light to be refracted. And then there's diffraction, is the spreading out of a wave through an opening or around an obstacle. And I intentionally put a picture in front of the word obstacle because the picture becomes an obstacle. But you can see in those pictures how the waves change as it goes through the opening. So we'll talk more about that in class. But these are general wave behaviors because they can work with EM and mechanical. Now we have to talk about production of visible light. There are 3 different types of production of visible light. Incandescent, which is the production by high temperatures. For example, the sun. I call it a regular light bulb, meaning the old school light bulbs that look like this. And fire is also incandescent. There is luminescence, which is the production of light without high temperatures. So my picture here is a glow stick, or a firefly uses luminescence. So does jellyfish. That's bioluminescence. That's luminescence produced by things that are alive. Fireflies would be in that same category. And then we have fluorescence, when a material absorbs EM radiation of one wavelength and gives off EM radiation of another. This is in neon lights, highway lights, some TVs and computers. Just a little factoid there with fluorescent rocks. You do not have to write down the fluorescent rocks thing. That is just some random trivia just to keep you interested. The next, we're going to talk about light wave behaviors. These 3 behaviors we focus on primarily on just with light, so that's why I label them light wave behaviors and not general wave behaviors. The first is transmission. This is the passage of an EM wave through a medium, this thing of a clear window. And the next is absorption, which is the disappearance of an EM wave into the medium. This is a really bad picture of SpongeBob. I used him because he absorbs water because he's a sponge. But I always think of it as you, for example, if you stand outside in the sun and you make a shadow behind you, you are absorbing all of the EM waves that are going into your body and they're not coming through you. And the last one is scattering, and this is the spreading out of light waves in all directions because particles reflect and absorb light. And I think of the ocean picture here shown that the light from the hits the top of the ocean and gets spread out, and you can see what it does in the water where The light waves aren't coming straight through anymore. Let's move on to the back. Talking about how wavelengths determine color. So the section of the EM spectrum called visible light, which is the fourth type, it's actually in the middle, is made up of many different wavelengths. And when all the wavelengths are together, the light appears white. That's why it's called white light. There's a tool called the prism. That prism uses the wave behavior of refraction to spread out the different wavelengths that make up white light. So the wavelengths all bend at different angles, forming a color spectrum called the rainbow, which you were taught a long time ago. And this is also how rainbows form in the sky, that the white light being produced by the sun is being bent, and that's where you see the rainbow from. And here's a picture of a spectrum, or a prism, a picture of a real prism. So there's a fake prism picture and a real prism picture. So when you see white light, it's actually full of color. Some people don't realize that. Now remember, we're talking about light and things in nature. We're not talking about paint. White paint is not full of all the different colors. Color reflection and absorption. So an object, what color it is determined by the wavelengths that it absorbs and the wavelengths it reflects. Meaning, if you see this yellow picture, an object, the color of the object is the wavelength that it reflects. So in my picture listed above, that white light hits that object like a yellow flower, and it absorbs all of the other colors and reflects only yellow to your eyes. Remember, we're not talking about paint. We're talking about things that are natural. And then there's some different extremes, if you want to look at it that way. Black objects absorb all colors and reflect none, meaning black with light is the absence of light. And then white objects reflect all colors and absorb none. This is why people tell you to wear white in the summertime, so you do not absorb more heat. And if you wear black in the summertime, you get warmer because you're absorbing more. And then there's some pictures on your notes that would be better if they were in color, but remember, you're in public schools and I can't afford color prints. And then the last thing is how materials transmit light. There's three different types of materials. There is transparent materials. They allow most of the light to pass through them. Think of like a clear screen or a bubble. And then there's translucent things, for example, like stained glass, or you can see my blocks there, which transmit some light, but they also cause it to spread out in all directions, making it look cloudy. And the last of which is opaque objects. These do not allow any light to pass through them because they either reflect light, absorb light, or do both. All right, make sure you have these notes and have any questions for me, and we'll talk about them when they're due in class.